Okay, I was asked to give a solution to this question here, number 10. First thing to note is there is a solution posted at the back. That's what the star means, but it isn't always as detailed or as complete maybe as a full explanation would be. So the first question here is asking me to find the coordinates of t given a parallelogram RSTU. So first thing to note, when the letters are listed in that order, it means that we can travel from R to S to T to U to get around the four vertices of the parallelogram. I'm given the coordinates of each of the vertices, and so what I need to know is basically what's happening along this path. What is vector RS specifically? And because it's a parallelogram, then vector UT will be the exact same vector. So if we look at RS, we're suggesting that our x value is increasing from 1 to 3. So basically the x value is going up 2, the y value is decreasing from 1 to negative 3, it's going down 4, and the z value is increasing from 3 to 6. Again, it's going up 3, and so RS is the vector 2, negative 4, positive 3. The math, of course, you recognize that the difference between them is what we're interested in each case. So 3 minus 1 is 2, negative 3 minus 1 is negative 4, 6 minus 3, so end minus start is positive 3. So because the shape in question is a parallelogram, UT will be exactly the same as this. And that means that, again, essentially in going from U, in going from this point to our end point, we have to increase by 2, decrease by 4, and then increase by 3. So basically, that's the U value. That's the point U. The point T will be this increased by 2, this decreased by 4, and of course I didn't give myself enough room. And the 7 increased by 3. And so our coordinates of t will be 0, 0, and positive 10. Now, once we know that, I think the rest of these are not going to be bad for a full solution. We want to find the measure of the interior angles. So the one thing to note here is dot product allows us to, or the dot product formula gives us a way to calculate an angle between the tails of two vectors. Okay, so if we kind of go back to the diagram here, the vector RS and the vector RU are the two that are being used. So again, the two vectors tail to tail, and we're going to calculate the angle between them. So R to S and R to U are the two vectors I want to use. RS is this one. RS is this one. And then to find RU, we can do the same thing we did before. From R to U, we need to decrease by 3. We need to increase by 3 and increase by 4. And so vector RU is negative 3, positive 3, 4. We can do the dot product then. And remember, there are two formulas for dot product. There's the one that has the angle included, and then there's the one that uses the components, the Cartesian components of the vectors. So 2 times negative 3 is negative 6, plus negative 4 times 3 is negative 12, plus 3 times 4 is 12. And so essentially this is making use of the second version of the formula, the one where A1 times B1 plus A2 times B2 plus A3 times B3, wow, is the dot product. That allows us to find an answer of -6 here, and these two values are the magnitudes of the two vectors. And of course, to find the magnitude of a vector, we simply use kind of a modified Pythagorean triangle, or Pythagorean theorem, excuse me. So 2 squared plus -4 squared plus 3 squared is going to be what? 4 plus 16 is 20, 29, so root 29 right here. And then using the other one, same sort of thing, square it, square it, square it. 9 plus 9 is 18, plus 16 is root 34, and then solve for the missing angle. You could do the same thing again with another corner, but because it's a parallelogram, of course, the sides that are adjacent to one another are complements, and so they must add to 180 degrees. Find the measure of the acute angles of the intersection of the diagonals. Okay, so if we sort of continue with this, maybe if I copy this to a new screen, what it's asking me to do is draw in the diagonals here and here, and then find, whoops, find the measure of the acute angles at the intersection. So basically determine what the smaller of these two angles is. Well, I guess what all of them will be in the end. Two of them, the ones that are across from each other will be the same, and of course these two will be the same as each other as well. And so essentially what we've got now is I've got two new lines put in that could be treated as vectors, and my suggestion is basically we do the exact same thing. So we can use, what did they use? RT and SU. So RT is this one, SU is that one. That's interesting. Okay, so I was caught a bit off guard by the vectors that they chose. My suggestion would be that if you chose vectors TR and TU, you could find this missing angle in here. Do the same thing going the other way with UT and US and find that missing angle. And then, of course, those two add to 180 to give you this one. Now, what they've done, and certainly nothing wrong with it, slightly more advanced than I would have necessarily come up with myself, honestly, is in recognizing that vectors can be shifted around. If we move vector SU up to this point here, so that it is now tail to tail with TR, we can use those two vectors to find this missing angle in here. And then if we look at what we've got, sort of this blue down through half of the red onto this one here, this is a Z angle because this and this are parallel. And so in finding this angle out here, we're actually able to find this angle as well, and then subtract from 180 will get us the missing angle here. Okay, so this is sort of what they tried to do with this one. They used RT and SU and did the exact same thing as in part B, and found the angle to be 85, the other angle 95 as a result. So sort of just again one last time, took this vector and slid it up in order to get the two vectors to be tail to tail. Finding this angle then allows me to state that this angle right here is exactly the same. And finally, part D here, find the area of the parallelogram. One of the things we saw in the video we saw by Mr. Richards, and one of the things and the same thing that was sort of written into the notes, was the fact that the magnitude of a cross product between two vectors. Here's vector v, vector u. If we find the cross product of those two vectors, we end up calculating the area of the parallelogram. And the reasoning for that is, if we think about what this section here is, v times sine theta. So if this is vector v, and we want to break it into its horizontal and vertical components, the vertical component is this value here, which is the height of our parallelogram. And so vector u is the base, sine of vector v, or sine times vector v, sine of theta times vector v is the height. Base times height, of course, is the magnitude of the parallelogram. And so this one's pretty straightforward. Cross product of rs and ru. Really, from any one of the vertices, this would have been fine, as long as, again, you had them actually both leaving the same vertex. So it's r and up, r towards s, r towards u. And again, just plugging in the numbers. These are the magnitudes, similar to the calculation here. Well, actually, the same as the calculation here. It actually is the same vector. The same vector as this one as well. And then times sine of the angle that we found in part B, I guess. Yes, part B. And that becomes the cross product of those values, which again is equivalent to the size of the area of the parallelogram. So I apologize, that was a little quick. I meant to make the video earlier. No, I'm not going to say all that. I'm going to stop